this is working. So I am gonna give you guys a little intro to lab exercise 3. This is Daphne. This is Niall's cousin. She's kind of shy, very loud and squealy. She's okay. So lab exercise 3, RC circuit response. So in this lab, we will be measuring the time response of the voltage across a capacitor in an RC circuit, such as that shown in figure 3.1. So this is the standard RC circuit that we've looked at before in class, in the mechatronics class. And we're going to look at the output voltage across the capacitor. We're going to supply the voltage, and we're going to measure the voltage with the MyRio. So your skills that you learned before will come back into use. And yeah, so we'll apply an input voltage and measure V out the response with the NI MyRio, export it to a data file. So last week, remember, we didn't actually record and log the data in the MyRio. We just learned how to write a VI, and we could display it, and then we wrote down the numbers. But now we're going to actually use the power of the MyRio to save those data points. So we're going to do that. We're going to plot, import the data. So capture it with the MyRio, export it to a data file, import that data file into MATLAB, plot the data, drive an analytic model, and compare the analytic model to the data. So the whole thing. The objectives of this lab exercise are for students to explore transient circuit response, so that's the first thing, to deepen their understanding of RC circuits, that's the second thing, to learn to acquire and log data with a microcontroller board, the MyRio specifically, 4, to learn to explore the acquired data to, or export the acquired data to MATLAB, and then to model real circuits and compare the theory and experiment. And finally, to learn to better plot and export plots in MATLAB. So those are what we're trying to do in this exercise. So hopefully you focus on those as you go through this. One thing to note, we're going to be applying to this RC circuit. We've done several things in class. We've applied sinusoidal voltages, for instance. But what we're going to do is actually apply a DC voltage, a constant voltage, but we're going to apply it suddenly, and the capacitor will be discharged to start, and then it will, of course, charge up as time proceeds. So we should be able to predict how it will charge up pretty well. So your theories and all the analysis that we've learned in class should work for this. So it's great. So materials, your usual stuff. You're going to use a 100 kilo ohm resistor and a 10 microfarad capacitor for that RC circuit. Start off by building the circuit. There's nothing too complicated about this circuit. It's just a resistor and a capacitor in series. Just make sure that you remember how the breadboard works and the connections running along the columns, the numbered columns. So once again, we're using the C connector of the MyRio. We're going to use it to supply voltage from analog output 1, I think I chose to use this week. And we're going to be measuring the voltage using the analog inputs. So both of them, actually. So these two to measure, I think, the output, and I think these two to measure the input. I don't remember for sure which one I chose there, but we're measuring the output and the input just to cover all our bases. It's good to do, even though you think you know what the input to the circuit voltage is because you've specified it on your analog output of the MyRio. It's good to double check that. It's good to always measure what that is. So even though you're setting it to be 10 volts, you always need to double check. And so that brings up a couple things. So first of all, there's an ambiguity in the terms output and input in a lot of these lab exercises, because we have the perspective of the MyRio. So here's the MyRio. And you have also the perspective of usually your circuit, right? Circuit. So the output of the MyRio becomes the input of the circuit, and the output of the circuit is measured by the MyRio, so it becomes the input to the MyRio. So it's good to be precise, and there's just, you have to look at the context. What is the context of saying output or input? Are we talking about the circuit? Is it the circuit's output, circuit's input, or are we talking about the MyRio's output or the MyRio's input? This ambiguity runs throughout, all the lab exercises. It's just part and parcel with doing anything with multiple devices, because you have an output and an input of each. So it just so happens we have this, symmetry where the output of one is the input of the other, and the input of one is the output of the other. It's just something we have to deal with. So it's fine. So make sure that you measure your resistor and your capacitor, because they're nominally 100K and 10 microfarads, but of course, as we learned last week, they're not always exactly the nominal values. In fact, they almost never are. So something to make sure you recognize as you build your circuit: the capacitor is polarized. So it'll have, we talked about this in class, but it's going to have minus sign symbols on the negative terminal, and it's going to have a shorter lead. So you're going to have a capacitor, blown way up. It's going to look like this, and you're going to have two leads coming out of it. One lead will be shorter, and also there's going to be a stripe down the side, and we're looking at it from the side, so we can't see the whole minus sign, but there are going to be minus signs running on this side. So that's the side you have to connect to ground. And the voltage has to drop from this terminal to this terminal, okay? So make sure you connect it that way. It's probably not going to be, so you should always wear, in the lab, you should always wear safety glasses. And even when you build small electronics, it's not likely, but it is possible that you're going to explode a capacitor. So especially if you flip this and run voltage across it the other way, and in which case you're going to get a nice pop, hiss, usually. Just depends on how much current you run also. So there's nothing surprising in here. It's just sort of going through the steps. When you build your LabVIEW VI, the front panel could look something like this. This is actually showing you a response. So this is showing you the input to the circuit stepping from 0 volts to 1 volt, and then the corresponding capacitor voltage rising. Looks a little exponential, doesn't it? Probably should be. That should be what your analysis shows. And this is actually these data points, all these data points making up this curve. Nice if I didn't use black, probably. I got a new edition of Illustrator and I can't find my colors. But in any case, this red curve has a bunch of data points in it, and so does the white curve, and we want to capture those, and that's what we're going to do. We're going to save that to a file. Okay, so when you build your VI, you should have a file name. I hate motorcycles. Did you guys hear that? That's crazy. I hate them. Okay, so file name. This is the path on the MyRio. So the MyRio actually has some storage on it, and you're gonna build your VI and type in your file name, and that's where it'll save the data to. So notice there's an execute button The execute button is going to be when you start the circuit. When you're going to do a transient response, you have to be able to time it, right? You have to be able to start taking data and capture the data and save that data from a starting execution. So once you've executed and you've got a nice response, you can see when it settles down. So wait until it's finished and then hit stop and save. So you have to build a VI that's going to do this for you, but once you've got it, it's pretty nice to work with. So I'll give you, so in here there are some detailed instructions. So I encourage you, as always, go through it. You notice I put these check boxes next to these numbers. Go by, check them off, go through one by one. It'll save you time in the end, because if you miss a step, it's not gonna work, and then you're gonna have to debug. So as with the last sample VI or example VI block diagram that I posted, this one is not quite what we want. It's close, but it's not quite. So what I'm doing here, so broad strokes, there's this stuff out here, and that is our initialization stuff. So this is all this initialization and initialization. And here, one of the things that we're doing is actually resetting. So when you run the VI, it resets all the values to initial values. And that's just kind of a nice thing. If you don't do that, what can happen is, so the execute button, when you click the execute button, it's going to stay on. You hit stop and save. If you don't reset it, then when you start the VI the next time, it'll just execute. So that's really annoying. So I put this initialization code in. It's not necessary, but it is kind of nice. So this is something, it's kind of optional, up to you if you want to put that in there. This is a timed loop. So this is something that I tell you like what the function palette is that you can find it in if you read through the instructions. But the timed loop is really nice because we could do timing sort of ad hoc, where we say, okay, wait 10 milliseconds inside the loop before moving on. But that doesn't take into account the execution time of the other code in the loop. So that can be variable, and also you might not know what that is. So in order to get a nice timed loop, what you do, and it doesn't guarantee that it's going to run at that frequency. So 10 milliseconds is the time that I set it to. This is not the timed loop timing. This is actually the clock time of the processor. So set that to 1 kilohertz. That's plenty for us. Our DT is going to be 10 milliseconds. So that means that in between time steps we have 10 milliseconds. We could probably even go longer, because the response is slower, isn't that fast. So that's pretty pedestrian, 10 milliseconds. We could do much faster if we wanted to, but that's plenty for us, and probably a little bit overkill. So the main loop is going to execute once every 10 milliseconds, unless the code inside of it takes longer than 10 milliseconds to execute, in which case it'll skip. And this is something that it's not always easy to detect that, to debug that, but for what we're doing, 10 milliseconds is a long time. So this MyRio can do these timed loops much faster than that. Can take these samples and put them in these arrays much faster than that. So that's no big deal. We shouldn't run into any issues with exceeding our 10 millisecond window for the timed loop. So it'll execute this timed loop. It'll execute all the code inside of it, and then it'll return, and it'll start again when it waits for that next clock tick. Okay, you think of it as being like tick tock, it goes around. So while it goes tick and it starts, right? So tick, and it's going to come in here. It's going to put out whatever the analog output is, one sample of it, and you specify what that is. So we're either going to put out 1 volt or 0 volts. And this block here is a true or false. So what it does is it outputs the top value, the true value, if the Boolean, the green line here, is true. and it outputs the false value if the Boolean is false. So we have this thing tied to a Boolean, an execute button. So it turns on the voltage output, and we're going to use that same Boolean to start taking data. So we'll talk about how it takes data in a minute. But the first thing it does is it puts the analog output, it switches it from being 0, which it starts off as false. When we toggle it, it turns it to true, and it puts 1 volt on this output, and that 1 volt goes into the analog output. Okay, so that's the first thing that we do. Then we're going to so one thing that's nice about execution, you know that the order of execution is going to follow this nice error pipe. So error pipes, it's kind of a detailed concept, but the main idea is that if you have an error arise from one of these, so say you try to execute a block, any of these blocks, and something errors out, like for some reason it can't do what you asked it, then it will have an error that will return in these yellow pipes, okay? Those errors act as, like at the end you want to display the error, and that's what we do. Actually, where did we display it? Down here, the error out. So this will show up on the front panel up here. The error out, it'll tell you what the error code was and where it came from. That's great. That's one good reason to have these error pipes. Another nice thing is that the execution order will follow the pipe. So if you want to, inside this block and this whole like GUI thing, we don't have lines of code. In lines of code, we know that this line will execute, then that line will execute, the next line will execute. In a GUI one with its block diagrams, it's harder to know which one's going to execute first. Sometimes that matters, and when that does matter, what you can do is daisy chain them. So have one, so have the error signal, error pipe go into the error in, and then the error out of the first one, and then go in and then out of the next one, and that guarantees the order of operation. It's kind of nice. So do that, and you're going to have then an analog input. So you're going to put out a voltage, and then you're going to sample a voltage. The difference between what I did on this example, what I want you to do, is that I want you to measure two things. I want you to measure not only, so this analog input is measuring the capacitor voltage, VC, or V out is what I called it. The output voltage of the circuit, and that's great. So if we were really confident in what our input was going to be from this analog out from the MyRio, we wouldn't need to measure it, but we should always measure that. We really can never be confident in what that's going to be. So we should measure what that input of the circuit was as well. And so I want you to have two of these analog input blocks. So I'm using AI0 here. You should also use AI1 from the C connector and get two measurements of voltage. Okay, so that's the main difference between what I did and what I want you to do. I want you to have two of these. Okay, that measurement, you're going to want to display it on a graph, okay? So that's the chart that you're seeing there, the voltage chart. That's what we're plotting here. That's this guy. You want both. You want both your input to the circuit and your output. So I just plotted, so what you do here is you concatenate them into one pipe, and then you put them into the waveform chart. And when I did that, I just took whatever the analog output was supposed to be, right? So I just took the nominal value. You should take the actual measurement. It should be real close, but it's good to do the actual measurement. So instead of taking it from this guy, you're gonna take it from your other analog input and graph it. You can graph all three if you want. That's totally fine. If you just select the bottom edge of this and you pull it down, it'll give you another terminal to put all three on. That's fine too. So you would do the command, the actual VS, and then the V out. Okay, so that's plotting the data. That's like putting it out. It's putting out your analog output. measuring and graphing, and that's all great, right? But we also are going to want to do some more things, right? Mainly, the thing that's tricky is we want to save the data. Okay, so the first thing to do is to actually keep track of it, because once you go back around this loop, you lose that last data point. The last data point's gone. So, okay, so this is the part where it gets a little bit. There's a little bit of nuance. That's where like most of the rest of this mess comes from. This is all just saving the data. What's happening inside the loop is I'm adding each data point to an array. Okay, so putting stuff into an array is the first thing you need to do. When you have an array in LabVIEW, you start off and you have to initialize the array. So you initialize it with zeros, okay? And then what you're doing, these things, these arrows, these are shift registers, and you should have learned about them in the first lab, but I will talk about them. They're a little bit confusing, I think, sometimes at first for people, but then you get more used to them and they're not so bad. So it goes in to the system, and essentially until you hit execute, this panel is going to be false. Okay, so I'm showing true here. False just passes those arrays right through. Okay, so I didn't show the false panel, but it's just blank, and all it has is these array lines just go right through. They just pass right through, and they get passed to the shift register. When you do that, what happens is the empty array goes around and it hits this arrow. So pointed up in a LabVIEW loop, shift register takes that value and it pushes it up and around. Okay, and so what it does is it pushes around to the next time around the loop. So it pushes it up and around, and it comes back here. So that same empty array that you started with, you initialized with this, comes back around, and it just keeps looping around empty, like all three of them. So we're going to do three because we want to measure the analog input, this one, the one that's measuring V out. We also want to measure the other one you guys are going to put in, the one that's going to measure VS. And you also want to measure the time step, okay? So those are the three things you want to measure. So you're going to have three arrays that you're going to keep track of. I kept track of, in this example, the nominal analog output. You should actually, instead of that, keep track of the actual measured analog output. So the other analog input that you're going to have. You should take that, the one that I'm taking here, and the time array. So those three arrays are going to be empty. Okay, they're just going to get looped around empty until you hit execute. Okay, when you hit execute, then it's going to flip this and it'll come to this true panel. The true panel is what it's going to do is it's just going to add a value to each array every time it gets executed. So what we're going to do is going to take each of our, I took the analog output, which you're going to take the measurement of that, the analog input, so your other analog input, and the time step, which we'll talk about in a second, and the time step, and you're going to put the value, the current value, into an array, okay, into that array that was initialized, and you're going to put it out, and it'll go back to the shift register. So what you're doing is just appending a value to it. So you have three of them, so you're going to have three shift registers here, and it's going to go boop back around, and you're going to go back through this, and this time, every time you go around the loop, you add a new data point. It's going to take a new data point every 10 milliseconds. Okay. So you are mostly you've got it now. Okay, so you've got your arrays that are taking the data. So you're holding it in memory. You haven't saved it to the disk yet, to the flash memory yet. So it's just in RAM memory. So it only lasts until you do the next thing. So it's going to hold it for now, and then if you stop executing the program, it's gone. So we're going to need to save it, and that's what all this stuff out here is. This is the save part where you save it to the flash memory. Before we do that, let's talk about time. So time we set this, it's every 10 milliseconds that we've got our loop going around. So what I'm doing here is I'm taking the 10 milliseconds, boop, boop, and I'm multiplying that by 0.001, which is to say I want to convert that from milliseconds to seconds. Okay, you don't have to do that. You can just know that your array is going to be in milliseconds, but I chose to do it in seconds. So I multiply it by 0.001. I also multiply it by the time step. But I want my time to start at 0. I don't want my time to start at like whatever, the 2 millionth time through that loop. I want to start at 0. So I have, just like I initialize this array, I'm going to initialize an integer, 0. I'm going to take that integer and just do the same thing with it. I'm going to add 1 to it only when I've hit execute. I add 1. So the first time I hit execute, the first time through, it's 0 plus 1, and it goes to the shift register. 1 is here, goes around, 1 shows up here, and now it multiplies here. So it's like your time stepper, right? So now time 0, now it'll be time 1 times 10 milliseconds times 0.001, so now it's in seconds. So I get 0.01 out, and that value is going to come in, and we're going to save that value. And every time through the loop, now it's going to be 2. Now this is going to be 2, so cancel the 1. Now it's going to be 2, and now every time through the loop, it gets a new plus 1. Okay, so that's our iterator, our index, okay? And finally, we want to save these things. We want to save, in particular, we want to save our the time, the output. And so when I say output here, when I label this, I'm specifically talking about the output of the MyRio, so analog output. Remember, that's the input to our circuit. And then the input, which is, of course, the output of our circuit. So it's weird, right? And what I'm doing is I'm putting the array values into this array save new file VI, and that's something that I give you. And if you read through this, it gives you a download link. Download the VI and import it into your project. And so you can just use that. So I didn't make you write that part. So what you're going to do is you're going to save the time array, then you're going to append to the same file your output array, and then you're going to also append your input array, and then reset the MyRio, put the error out, and you're done. So that's the VI. It's a little bit more complicated than last time, you might notice, but this is a really useful sort of VI. This is a VI that you can it'll put hair on your chest. I don't know. It's a good VI. It's a good VI. So the only other thing that has to do that we have to talk about is that file name. So file name is another type of function palette object you can grab, and it will produce this here. And you can actually browse when you run this VI. You can actually browse and look at the where you want to save it. I recommend saving it in C data, and then just name it whatever you want. Data file 001. Make sure that you note what you named it, and make sure you get that file. Because if you get the wrong file when you pull it off of the MyRio, then you're going to be disappointed when you import it into MATLAB. And I encourage you to actually do the MATLAB part. So you're going to do this. You're going to get data out, and it's going to take less time than you think. You're actually going to get this written. It's not going to take you forever, and you're going to get this done, and you're going to capture the data. That takes like a second, right? Or a few seconds. This whole thing takes a few seconds. So it's not going to take that long to actually capture the data, and then you're going to stop and save, and then go looking for your data file. So I have a description of that. When you get down here, it says read. Wait. Before you do that, you have to prepare the MyRio, which you have to do that. But capture this, and then it tells you how to find your data file. So see if that is in the place that you're looking for it. It should be named the thing that you named it. Name it something unique too, because then you'll know that it wasn't, if you just do data file 001, then somebody else might have saved it there and it might not be your data. And if it's not your data, it might be crappy. So keep that in mind. Okay, so, and also it overwrites old stuff that was there. So whatever your file name is, if you don't want to wipe away the old one that you did, make sure you rename it in the front panel before you hit execute, or execute. So then get it, so copy that off onto the computer, and then I have one of the resources down here. So, oh, well, it's not in here, but one of the resources, which, here, let me pull it out for a second. There. Whoops, that's not what I want to do. So chapter 3, that's the one I'm looking for. So I encourage you to go through both resources before you leave the lab. But this one, so one of resource 5, you need to go through while you're doing it, while you're doing the data capture. But I would encourage you to go through resource 6 and actually do this part before leaving, because then you can get help with it if you run into issues. So you're gonna have this .lvm file that you'll get from the MyRio, and you're gonna copy it onto the computer. Now, before you leave, you should check that LVM file. I've had this happen before where people leave the lab, they'll have their LVM file, and then they'll actually import it, and there won't be any data there, or it'll be garbage data. So make sure that you do this before you leave. So get this and extract the contents of the zip. This is going to be an M file. So I give you all the steps to import the data from this LVM file that LabVIEW exported, and import it into MATLAB. So, and I go through, because it imports it into a struct class, which is not something that you guys probably have seen a lot of. You may have encountered it in the past, but most likely you haven't. So what I do is I show you how to take the 3 arrays that you saved into that data file and extract them out into arrays. So go from struct to arrays, and this shows how to do that. So then you can plot, and I even show you an example of how to plot using those arrays, which might have been holding your hands too much in retrospect, but in any case, that's a place to start. And I would recommend you do that. There's MATLAB on those lab computers, on your lab station, so go ahead and you know, save yourself a lot of trouble and do it while you're in there. Okay, that's all I've got. So good luck, have fun, don't forget that, and yeah, see you guys soon.